Okay, we'll go ahead and start. Today we're going to do L1, which will be our first lecture on lipids. And of the three major sections, protein, carbohydrates, lipids is probably the easiest and to some people the most interesting because generally not a lot of background with lipids. So lipids. Lipids are generally insoluble in water. And as you guys know, they are an important source of energy. So per gram, they provide a lot of energy, and that is important when you need energy. As you also know, they are a component of the cell membrane. So we have to get across the lipid bilayer. And this lipid bilayer is going to be an important source of lipids in cattle from the microbes. Maybe not as important in Texas as Montana, but they also provide insulation. They keep you warm. They supply essential fatty acids. So in terms of nutrition, the essentiality of fatty acids is relatively new. It was really new when I was a grad student, and before that we didn't think they were essential, but you actually require some fatty acids in your diet. Your body can't synthesize them, so you have to have those essential fatty acids in your diet. It's also important for the synthesis of hormones. We need to absorb, so they're crucial for the absorption of fat-soluble vitamins. And something else that we all know to be true about lipids, but especially for humans and pigs, to some extent, they're very palatable. Horses and cattle don't maybe like them as much. Cattle for sure don't, but they're palatable. So they're important for palatability. And we use them sometimes to condition feed. Makes the feed bright and shiny and decreases dust. Okay, what we're most interested in is fatty acids. And fatty acids are straight chain hydrocarbons. They terminate in a carboxyl group. Okay, and they are from 4 to 24 carbons. And in general, they look like CH3. This would be a saturated fatty acid. CH2 to the N, and being a number. So somewhere between 2 and 22. And a carboxyl group. And so these fatty acids are a component of complex lipids. Okay, within that, or within fatty acids, We have two types of fatty acids. We have, scoot up a little bit. We have saturated fatty acids, which we will abbreviate as SFA. And if this was a normal class, this is where we talk about Stephen F. Austin and Nacogdoches and how their mascot is a lumberjack, and they say Axum Jacks, and I think it's funny that their mascot is a lumberjack, and their campus is covered completely in trees. But this is not a normal semester, so you will miss out on that story in person. So saturated fatty acids contain no carbon-carbon double bonds. They're completely saturated in that they have as many hydrogens in there as they possibly can have. And so write that in red. They contain all of the hydrogen they can possibly hold. Okay, so if saturated fatty acids are one, the other would be unsaturated. And we're going to abbreviate unsaturated as UFA. We're going to underline them just to make sure we know that it's not a VFA. So unsaturated fatty acids, they contain one or more carbon to carbon double bonds. Okay, and so in red, we'll write two things. We will write that they are missing two hydrogens per double bond. Okay, so if I have a fatty acid with 20 carbons in it and it has no double bonds, it has all the hydrogens it can. If it has two double bonds, I know it's missing 4 hydrogens. Okay, and double bonds, that's an O, double bonds exist in cis or trans configuration. And so cis, they point the same way, trans, they point across. Okay, within unsaturated fatty acids, there are two types. There is mono unsaturated fatty acids, which would be MUFA. And they contain one carbon to carbon double bond. And then we have polyunsaturated fatty acids, and those are PUFA. And they contain two or more carbon to carbon double bonds. Okay, and so double bonds are crucial because they're important for membrane fluidity and so they allow membranes to maintain a fluid structure and increase permeability. And so with more double bonds, you decrease melting point. And so oils have lots of double bonds and they are liquid at room temperature. And fats equal solid at room temperature. And so at our house, we are entering the time of year where butter, because we keep butter out on the counter so it's soft, in the winter, because we keep our house relatively cool, butter is a solid. In the summer, we keep our house relatively warm, and our butter takes on kind of a semi-solid oily thing because we're pretty close to its actual melting point where it becomes a liquid. So oils, lots of double bonds or more double bonds. And fats, few double bonds. So you can look at a fat, and based on how hard or firm it is at room temperature, you can tell how many double bonds it has. So if you've taken meat, sometimes, or at least back in the day, they would talk about soft bacon. So if you feed pigs lots of unsaturated fatty acids, you can change the composition of the fat in the bacon, and that will make the bacon fat or the bacon soft. If you feed them lots of saturated fatty acids, the bacon stays firm. Okay? And so we don't have the same effect in ruminants because, as you guys may guess, the ruminal microbes are going to alter the fatty acids and make them more saturated. So the fat in ruminant animals tends to be harder. Okay. Now we're going to do nomenclature. Generally, there's a nomenclature test question. But there's probably not going to be a nomenclature test question per se, because it's basically just memorizing how to do something. But we're still going to discuss it. That way you guys know how to do it, and I know you guys know how to do it, and then I can sleep well. So you still need to pay attention. Don't fast forward me. I might tell a real funny joke and you'll miss it. So, fatty acid nomenclature. There are two systems. Okay, the first is the delta system. And the delta system is mainly used by chemists, whereas the other will be mainly used by nutritionists. Okay, the delta system, basically we have 18 to delta 9, comma 12. The 18 equals the number, that means number, it doesn't mean hashtag, it means number. 18 equals the number of carbons. Okay, 2, the 2 after that tells us the number of double bonds. And then the delta 9, comma 12 informs us that the double bonds occur at carbons 9 and 12. Okay, and numbering starts at the carboxyl end. Okay, the other system is the omega system, and so it looks like a W or an N. So those are the abbreviations we're going to use. This is like omega, and because nutritionists can't make the omega sign, we just use N. Okay, so we have the 18, we have a 2, and then we have an N or omega 6. 18 equals the number of carbons again. So some similarities. 2 equals the number of double bonds. And omega 6 tells us double bonds occur at carbons, because we know there's 2, so it's carbon 6 and 9. And this is the most confusing thing about this, is we can get the 6, right? And you guys can see 6, so that makes sense. It starts at carbon number 6. The 9 is the hard part, but in this system, because this system is based on nutrition and nature, the double bonds are always separated by 3 carbons. So when you have 18 to omega 6, you know the second double bond occurs at carbon 9 because it's separated by 3 carbons, so just add 3 to it. If we had 3 double bonds, they'd be 6, 9, and 12. Okay, the other difference between the omega system and the delta system is the numbering. Starts at the methyl end, okay, or the omega end, alpha and omega. The last carbon's the omega carbon. Okay, an example. Okay, we have linoleic acid, and it is an essential fatty acid, and it is 18 to delta 9, 12, or if we're naming it using the omega system, 18 to omega 6. Those are the same fatty acid. This one's just named by the delta system. This one's named by the omega system. So what we need to be able to do is we need to be able to sit down and draw it out. And so you have CH3, should be the omega carbon or the methyl carbon. This is methyl, not methyl. Yeah, it is the methyl. Okay, because it is a methyl group. And so then we have CH2, 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 and then this, so this is carbon 1, carbon 2, 3, 4, 5, and we know there's a double bond at carbon 6, so CH, and so we're removing a hydrogen because a carbon can only have 4 bonds, and so carbon 7, and then carbon 8 is a CH2, so 8, and then we do number 9, we know it has another double bond, and then so 9, 10, CH2, 11, CH2, 12, CH2, 13, we're going to run out of room, CH2, 14, CH2, 15. They're not really supposed to have a turn in it. 16, CH2, 17, and COOH is carbon 18. So it doesn't really bend. We just ran out of room. Okay, and so this is the carboxyl end, or the alpha carbon. If we're numbering according to the delta system, this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is important because we said there's a double bond at carbon 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So red numbers equals the delta system. Blue numbers equal the omega system. Okay, and if you want to write it out easier, you can write, so this is the same thing, CH3 scooted over and up, CH3 bonded to CH2, 4, so that gets rid of the first 5 carbons, then CH double bond CH, CH2, carbon 6, 7, and 8, bonded to CH double bond CH, bonded to CH2, 7, and then COOH. These are carbons 8, 9, and 10, and then this would be carbon 18. That's probably the easier or shorter way to write it and makes it fit on your paper. And in the omega, or in the delta system, this is carbon 9, 10, 11, 12, and 13, and 18. Okay, so that's the same one, just in a shorter form. We will do one more, and this is the other. So we said this is an essential fatty acid. This is the other essential fatty acid, and it is alpha linolenic acid. And so it is an essential fatty acid. And it is 18,3 delta 9, 12, or 15, or 18,3 omega 3. So those tell us it's the same thing. Okay, they mean the same thing, just the delta system versus the omega system. So we come down and we write CH3 bonded to CH2, and so this carbon 1 using the omega system, this is carbon 2. So then we know at carbon 3 we have a double bond, so 3, 4, CH2, 5, and so we know because it's 3 carbons later, so you add 3, another double bond, and there's 3 double bonds, so again 8, and then at carbon 9 we have a double bond, CH, that's carbon 10, and then CH2, 7 of those, COOH, gets us to carbon 18. If we want a number using the delta system, this is 1. So this is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So those are the essential fatty acids, alpha-linolenic and linoleic acids. Okay, we're doing quite a bit, but we will keep going. I want to show you something real quick, maybe, if I have it. I do have it. Probably not going to show up most amazing on here, but this is posted on eCampus, like in the materials that you should print before the class actually started. And so these are all the common naturally occurring fatty acids that we would think about feeding: stearic acid, palmitic acid, stearic acid, arachidic acid, lignoceric acid. Here is their formula, and then here's their notation. And so here they are again using the delta system and the omega system. And so it's not going to show up the best on here, but you guys can look at those. In a regular semester, I would say you need to know this, and you need to know their names, and you need to be able to write out their formula. You do not need to know where they come from in a diet, but you do need to know also that linoleic and alpha-linolenic are essential. So know column 1, column 2, and column 3. Okay? Okay, what we're going to do next is triacylglycerides. Triacylglycerol, or TAG, is how we will abbreviate it. It's triglycerides. Is kind of the more common thing in discussions like on the news or at the doctor's office. And this is how most lipid is stored. Okay, so in your body, this is how you store lipid, and approximately 95% of the lipid in your diet is TAG. And so what TAG is, TAG equals a glycerol backbone plus 3 fatty acids attached by ester bonds. And so glycerol has 3 carbons, an OH on each of the carbons, and then a hydrogen, and so that's glycerol. Okay, and then we have 3 fatty acids, and this is the basic structure of the fatty acids, which we've kind of just spent some time talking about. And so we're going to have 3 of those. Oh, sorry. When we form TAG, what's going to happen is we're going to remove 3 waters. And so we are going to form a glycerol. So write our glycerol. And so this glycerol is now going to be attached to 3 fatty acids. Oh. Okay, well that's not a complete deal breaker. Looks like that. And so we have our 3 fatty acids on there. This is now a TAG. And so with our TAG, we have 3 ester bonds. So we have ester bonds. And so when we think about digestion, we're actually going to do the opposite. So TAG digestion equals the hydrolysis of ester bonds. And you're going to do that by adding 3 waters. Okay. One other important thing we need to get at in this drawing is this carbon is SN1, SN2, and SN3. Okay, so that kind of gives us a triglyceride, carbons SN1, SN2, SN3, ester bonds, and then a fatty acid. What we're going to be most concerned about with digestion is breaking those ester bonds with water. One other lipid we're going to introduce, and that is the phospholipid. And we've talked about phospholipids before. They are what makes up the lipid bilayer of the cell membrane. And so we have an H, or a glycerol. So we'll have a glycerol again. And this time at the SN1, we're going to have a fatty acid. But what we're going to know about this fatty acid is it's generally a saturated fatty acid. At the SN2 position, we're going to have another fatty acid, and it is typically a MUFA or a PUFA. And this is where unsaturated fatty acids become important because they work in our phospholipids or in the lipid bilayer to make a somewhat fluid membrane. It's not a hard fat like if we had a bunch of triglycerides with saturated fatty acids. In the SN3 position, we have the polar head group, which includes the phosphorus, which is where we get the phospholipid, and a polar head group. Okay, and so on the lipid bilayer, the polar head group is what faces out towards the lumen, and it also on the other side would face out towards the inside of the cell. Okay. Oh, ceiling fan work. I think we'll go ahead and stop, make sure, and have a good day.